Here we go. We just took a quiz, literally, over the concept of exponential functions. So the general equation being y equals a times b to the x. And one of your equations, or one of the situations on the quiz that you did, was looking for how much time would it take for your money to double or for your money to do whatever. And really, the only way that you know how to solve that, looking for that exponent, is strictly by guessing and checking. You just had to plug some numbers in. Some of you used a table trying to figure that out. Now we enter into logarithms, and the logarithms are what help us find that missing exponent. So now if we're looking for how much time, if we're looking for an exponent, we no longer have to pull out our calculator and do a bunch of guess and check. We can use a logarithm in order to help us solve for that missing exponent. So a logarithm actually is the exponent. Logarithm and exponents go hand in hand. So this lesson that we're going to be looking at today is how we're going to rewrite from logarithmic form into exponential form into logarithmic form. But before we get started, I want to introduce you to my friend Log. Everybody say hi. Log. Hi, Log. Okay, so this is Log. Log never goes anywhere without its base. And then tagging along as well is y and x. So this is read as the log base b of y equals x. Log base b of y equals x. The log is short for logarithm. And remember, a logarithm helps us to find a missing exponent. Written into exponential form is b to the x equals y. So we're going to learn how to go back and forth from one to the other. Now, before we do that, you are going to get non-textbook instruction on this. And I am very proud of my non-textbook instruction. You will not find this on any page of any textbook. You're not going to find this out on the internet. This is AKA Math with Meyer at its best. So, when you're dealing with logs, you remember, once a base, always a base. I didn't know that was funny. Once a base, always a base, because we have a base of an exponent, that would be a logarithm. The base of a logarithm is going to be the same thing as the base of the exponent. So once a base, it's always a base. Next thing you need to know, you start with the base. You start with the base. And just in case you've missed it, it's all about the base.
I cannot read your handwriting today.
Okay?
It's not you, but I just can't read.
It's all about the base.
No trouble.
None. So once a base, always a base. You start with the base. It's all about the base when we're dealing with logarithms. Okay? So knowing that, let's go into our rewriting. Now, to rewrite, we need to practice our drawing skills, and I'm really not kidding. So here we go. Tell me if you know what this little creature is. It's a snail. Absolutely. It's a snail. And that's why we have snails up here. Because, and I would literally need you to draw a snail on your paper. Because we are going to discover how to rewrite using a snail method. And I really don't think that you're going to find this anywhere else, snail method. And if it is, then I apologize, but the snail method. And we use that to rewrite from logarithmic to exponential form and from exponential form into logarithmic form. And it tells us the order in which we write our numbers, okay? So let's just jump straight down to example 1. It says to rewrite the logarithmic equations in exponential form. So I have the log base 2 of 32 equals 5. All right? Now please understand, we're not solving anything. We're not out to prove anything. We're only rewriting it into exponential form. So our directions above say start with the base. So here's the base. The base is 2. Once a base, always a base. So I start with the base, and the snail method is where I start with the base and I will snail around until I end up at the 32. All right? So I snail it around until I end at 32. Once a base, always a base. So the base of the logarithm becomes the base of the exponent. I start with the base. So I go 2 to the 5th power equals 32. And on your calculator, if you so choose, 2 to the 5th power actually really does equal 32. I'm not joshing you. B. Once a base, always a base. Start with the base. Snail around. The 5 becomes the base. 0 becomes the exponent. Equals 1.
There was so much of this on the ACT.
10 to the 1st power equals 10. D, 10 to the -1, and anytime we have a negative exponent, that means we take the reciprocal, so that equals 1/10, or 0.1. 1/2 raised to the -1. Anytime I have a negative exponent, that means to take the reciprocal, and that equals 2. So that's logarithmic to exponential. So if something's in logarithmic form and I need to solve for it, I can rewrite it into exponential form to help me solve. And then the reverse of that works as well. If I'm in exponential form, I can rewrite it in logarithmic form using the exact same method. But I have to start out saying log. The base of the exponent now becomes the base of the log. And I snail around, giving me the order in which I write my numbers. So log base 3 of 9 equals 2. Log base 5 of 5 equals 1. Log base 1/2 of 4 equals -2. And log base 19 of 1 equals 0. Those two, example 1 and example 2, is strictly rewriting. And the snail method helps us to rewrite from one form to the next. Okay? From one form to the next. Logarithmic to exponential, exponential to logarithmic. That's all we did was rewrite. Now, we're actually going to evaluate. And we're only going to do the first 2 on here. Number 1 for time purposes, but the others I'm scared are going to confuse you off the top. We're going to come back at another day and finish up the others. But on A and straight across on E, I want you to say equals to X. Set that equal to X. And I'm in logarithmic form. So in order to solve a problem in logarithmic form, I'm going to rewrite it into exponential form. That's why we can go back and forth. It's there so that we can have a solution. If I don't know it in logarithmic form, I rewrite it in exponential and vice versa. So I'm in logarithmic form, so I'm going to rewrite it as 3 to some power is going to equal 81. And this is similar to our exponent quiz that we just had, exponential growth quiz or decay quiz. And we had to do a little bit of trial and error. Today's homework, you might do a little bit of trial and error. Tomorrow's homework, you better have a calculator because we're going to figure out how to do this. Mrs. Meyer, you said that it's so we don't have to do trial and error. Well, we're building up to that, okay? So right now, somebody that has a calculator, I want you to tell me how many times do you multiply 3 until you get 81. So 3 times 3 times 3, how many times? So x equals 4. So that's 3 to the 4th equals 81. Or log base 3 of 81 equals 4. You could look at that either way. Do the same thing on e. So you look at 4 to some power is going to give me 64. 4 times 4 times 4 times 4. How many times do I have to multiply 4? How many? 3 times. Perfect. 3 times. That's the concept you'll need to get your homework completed for tonight, okay? These, right now, I think will just kind of confuse you, so we're going to put those on hold and we'll come back to them, okay? Now, I want you to jump down to the bottom. And I want you to tell me, what is this symbol right here? It's a root. Get more specific with me. That's a square root. All right? What is that? That's a cube root. Well, wait a second. I have a question for you. If this is a cube root, that's a square root. How come this doesn't have a number?
Because it's assumed to be square roots.
It's assumed to be a square root, but what number do we assume to be here?
2.
Perfect. So are you telling me, you know I'm leading up to something here, are you telling me that we have mathematical symbols that we assume numbers to be there when they really aren't?
Never. I'm never telling you that. 'Cause I don't know myself.
Is that what you're telling us?
I'm telling you, because a square root, we normally don't see it with the 2, do we? No. Look at your calculator. Locate the logarithmic button. Everybody see the LOG button on your calculator? Okay. That log button right there has an assumed base of 10. This button here has an assumed base of 10. It is called, look at this first bullet right here, a common log. And I cut off that word logarithm. It's log base 10. Log base 10 of some number x is the same thing as log x. You don't see it written with the 10, but when we see just log written, we assume it to be with a base of 10. And only can I use this button when I have a base of 10. So these problems that we have above, the way that they're written and the knowledge that we have today, you cannot use this button to solve that. Now, for those of you that will be back tomorrow, which I'm hoping is every single one of you, we are going to find the trick on how to use this button right here to solve these logarithm problems right here. Okay? But for now, let's take it simple. On your calculator, type in log 5 and tell me what you get. And we can I just rounded it to the easiest one, 0.699. Do the same thing for log 7. And you should get 0.845. Typing that into your calculator. And again, that's assuming there's no base there That's a base 10. I don't mean there's no base. There is always a base. It's a base 10. Okay? Now, we've been playing around with this ln button to get to our e to some power button, because typically the e to some power is right above the ln button. Okay? Ln stands for natural log, not degenerate. Okay? It's not ln degenerate. It's the ln meaning natural log. Okay? Thank you, Jacob. I appreciate that. That is stands for natural log. Natural log also has an assumed base of e. The number e. Only in math do we have numbers as e and b as e and all that other stuff. But it has a base of e. We're going to treat just natural log without a base as well, like what we did with the logarithm. So just on your calculator, take ln and then 0.1, so natural log of 0.1. It would always helps if your calculator's turned on.
Yep.
Uh-huh. And you get a negative 2.3.
Especially when you feel like doing math.
Uh-huh.
Please excuse the interruption. JV baseball is canceled. Practice is at 2:15.
Okay.
JV